Okay, hello everyone. There are only 4 students attend the online class. I don't know the reason. Let's wait for a while. Only 4 students. Okay, 5 students. Okay, today we will talk about IPv6. IP has been in heavy use for decades. It has worked extremely well, as demonstrated by the exponential growth of the Internet. Unfortunately, IP has become a victim of its own popularity. It is close to running out of addresses. Even with CIDR and network address translation, using addresses more sparingly. The last IPv4 addresses are expected to be assigned by ICANN before the end of 2012. The only long-term solution is to move to larger addresses, IPv6. It is a new generation of IP protocol. It is a replacement design. IPv6 uses 128-bit addresses. A shortage of these addresses is not likely anytime in the foreseeable future. However, IPv6 has proved very difficult to deploy. It is a different network layer protocol that does not really interwork with the old version, IPv4, despite many similarities. Now we will look inside of IPv6. In 1990, IETF, Internet Engineering Task Force, started work on a new version of IP that never run out of addresses, because the length of address is 128. Then the address space is about 2 with the power of 128. So the network address, the space about about 128 is a square of 2. It is a very, very large. It's very, very large. So, and it'll be more flexible and efficient as well. Its major design goals were listed as follows. Support billions of hosts, even with inefficient address allocation. Reduce the size of the routing tables. Simplify the protocol to allow routers to process packets faster provide better security, pay more attention to the type of service, particularly for real-time data, aid multicasting by allowing scopes to be specified, and make it possible for a host to roam without changing its address. Allow the protocol to evolve in the future, permit the old and the new protocols to coexist for years. These were the design goals of IPv6. Support billions of hosts. So now this is the data is about 32, so 38 square of 10, 2.6 times 2.6 to approximately square, 2.6 times 38 square of 10. Okay, so very, very large address space. First and foremost, IPv6 has longer addresses than IPv4. They are 128 bits long, which solves the problem that IPv6 set out to solve. The shortage of addresses. This is the problem. To solve the problem, that means the shortage of IP addresses. Providing an effectively unlimited supply of Internet addresses. This second major improvement of, this is the first, right? This is the first. Provide effectively unlimited supply. The second major improvement of IPv6 is the simplification of the header. It contains only 7 fields versus 13 fields in IPv4. So simplify the header of IP packet. This change allows routers to process packets faster and thus improves throughput and delay. So improve the performance of the router. The third improvement is better support for options. This change was essential for the new header because fields that previously were required are now optional, because they are not used so often. So the optional. A fourth improvement. Fourth, represent a big advance is in security, authentication and privacy. Authentication and privacy are key feature of new IP. Finally, more attention has been paid to quality of service, QoS. Quality of service. Various half-hearted efforts to improve QoS have been made in the past. But now, with the growth of multimedia on the internet, the sense of urgency is greater. So the quality of service has been paid attention to quality of service. So the new property of IPv6 includes large limited supply of internet addresses, simplification of header, simplification of the IP header, better support for options, better support for security, pay more attention to quality of service. So in the final examination, if I have this kind of questions such as the properties, please list the properties of IPv6. Here, it is the answer. Okay. IPv6 header is shown in figure 56. So 56. It has these fields: version, differentiated services field, flow label, payload length, next header. Next header is the improved of option field. Hop limit, TTL. It is just like TTL. Then source header, source address, destination address. So it is more simple than IPv6. Then you should understand each field's meaning. The version field occupies 4 bits version. Here, IPv4 has the field 6. Differentiated service field, originally called traffic class, is used to distinguish the class of service for packets with different real-time delivery requirement. Flow label field provides a way for a source and a destination to mark groups of packets that have the same requirements and should be treated in the same way by the network, forming a persuaded connection. For example, a stream of packets from one process on the certain source host to a process on a specific destination host might have stringent delay requirement and thus needs reserved bandwidth. Then the flow can be set up in advance and give an identifier. This is what the flow label can do. Then follow the payload length. This field tells how many bytes follow the 40-byte header. Payload length. This is 40 bytes, right? 40 bytes. 40 bytes. 40 bytes is the header, 40 bytes. So the payload length tells how many bytes follow the 40-byte header. The name was changed from IPv4 totalness field because the meaning has changed slightly. The 40 header bytes are no longer counted as part of the length. The next header field tells the next header comes from the additional optional extension headers. Next header field tells which of the 6 extension headers, if any, follow this one. If this header is the last IP header, the next header field tells which transport protocol handle to pass the packet to. So the next header indicates which transport protocol handler to pass the packet to. Then hop limit is something like time to leave field in similar to time to leave field in IPv4, namely a field that is decremented on each hop. In theory, in IPv4, it was a time in seconds, but no router used it that way. So the name was changed to reflect the way it is actually used, with the unit of hop, not seconds. Next come the source address and destination address fields. A fixed length of 16-byte addresses, which would never run out. A new notation has been devised for writing 16-byte addresses. They are written as 8 groups of 4 hexadecimal digits with columns between the groups like this. This is a new notation for IPv6. Hexadecimal digits with columns between the groups. Since many addresses will have many zeros inside them, 3 optimizations have been authorized. First, leading zeros within a group can be omitted. So 0, 1, 2, 3 can be written as 1, 2, 3. So the leading 0 can be omitted. Second, one or more groups of 16 0 bits can be replaced by a pair of columns like this. So the one or more groups of 16 0 bits can be replaced by a pair of columns. Finally, IPv4 addresses can be written as a pair of columns and an odd dotted decimal. number. For example, like this. A pair of column. The IPv4 addresses can be written as a pair of column and a old dotted decimal notation. Dotted decimal notation. For example, like this. So this is 3 optimization have been authorized for writing IPv6 addresses. Perhaps it is unnecessary to be so explicit about it, but there are a lot of 16-byte addresses. Specifically, there are is 128 square of 2 of the addresses, which is approximately 3 times 38 square of 10. So if the entire Earth, land and water were covered with computer, IPv6 would allow 7 times 23 square of 10 IP addresses per square meter. Student IPv6 would allow this number IP addresses is very, very large per square meter. We can have these addresses, so it is nearly unlimited space of address. In short, it seems unlikely that we will run out in the foreseeable future. This is the advantage of IPv6. It is instructively to compare IPv4 header. Compare IPv4 header with IPv6. This is IPv4. We know version, header length, differentiated service field, total length, identification, DF, MF, fragment offset, time to leave, protocol, header, checksum, source address, destination address, optional. This is the IPv4 header. This is IPv6 header. So IPv6 simplified the IP header. So IHL field, header length, internet header length, IP packet header length is gone because IPv6 header has a fixed length. So it's gone. The protocol field was taken out because the next header field tells what follows the last IP header. All the fields relating to fragmentation were removed because IPv6 takes a different approach to fragmentation. As to start with, all IPv6 confinement hosts are expected to dynamically determine the packet size to use. They do this using the path MTU discovery procedure. Finally, checksum field is gone because calculating it greatly reduces the performance of the router. So with the reliable networks now used, combined with the fact that the data link layer and the transport layers normally have their own checksum, a value of yet another checksum was deemed not worth the performance price is extracted. So this field are gone. IPv6 introduces the concept of extension header. These headers can be supplied to provide extra information, but encoded in an efficient way. Six kinds of extension headers are defined at present as listed in this figure. IPv6 extension headers. For example, hop-by-hop destination options, routing, fragmentation, authentication, encrypted, security, payload. These six kinds of extension headers are defined at present. Each one is optional. But if more than one is present, they must appear directly after the fixed header, and preferably in the order listed. So in the order from the hop-by-hop to the authentication, encrypted, security. In addition to IP, which is used for data transfer, the Internet has several companion control protocols that are used in the network layer. They include ICMP, ARP, and DHCP. In this section, we will look at each of these in turn, describing the versions that corresponds to IPv4 because they are the protocols that are in common use. ICMP and DHCP have similar versions in IPv6. The equivalent of ARP is called NDP for IPv6. Now here we begin to talk about the ICMP. ICMP means the Internet Control Message Protocol. When something unexpected occurs during packet processing at a router, the event is reported to the sender by the ICMP protocol. It is also used to test internet. In the experiment 2, we use the command pin, right? Pin. That is, pin is based on ICMP protocol. So it's also used to test the internet. About a dozen types of ICMP messages are defined. Each ICMP message type is carried encapsulated in the IP packet. And the most important ones are listed in figure 60. Here, message types, then the description of the function. Destination unreachable. The packet when the packet could not be delivered, then a message, an ICMP message sent back to the sender with this kind of type, destination unreachable. If the TTL field hits 0, then use the message type time exceeded. Then the parameter problem, source quench, redirect, echo, and echo reply, timestamp, request, reply, router advertisement, etc. Then the destination unreachable message is used when the router cannot locate the destination, or when a packet with the DF bit cannot be delivered because a small packet network stands in the way. And then the time exceeded message is sent when a packet is dropped because its TTL counter has reached 0. This event is a symptom that packets are looping, or that the counter values are being set to null. This is time exceeded. One clever use of this error message is the traceroute utility. Okay, in the experiment 2, we use the command traceroute to find the path of a certain packet, from a source to a destination. We use the traceroute. So it's one clever use of the error message is traceroute utility that was developed by Van Jacobson in 1987. Traceroute finds the routers along the path from the host to a destination IP addresses. How does the traceroute utility do? It finds this information without any kind of privileged network support. The method is simply to send a sequence of packets to the destination. First, with First with TTL of 1, then a TTL of 2, 3, and so on. The counters on these packets will reach 0 at successful routers along the path. This router will each abundantly send a time-exceeded message back to the host. From those messages, the host can determine IP addresses of the routers along the path, as well as keeping statistics and timings on part of the path. So this is a clever use. Of this arrow message. So we can use a pin, and we can also use traceroute to test the network. And it's not what the time-exceeded message was intended for, but it is perhaps the most useful network debugging tools of all time. The parameter problem message indicates that an illegal value has been detected in the header field. This problem indicates a bug in sending host IP software and possibly in the software of a router transited. Now, we will not introduce other message types in details. So, ICMP is very useful for managing the errors in the network or for test the network. Then we will talk about ARP. ARP means Address Resolution Protocol. We know IP, the network layer, is over link MAC, right? Is a MAC layer. This is a physical layer. Data link MAC, then network there is IP, then transport layer, right? So IP addresses are not sufficient for sending packets. Data link layer, such as Ethernet card, do not understand internet addresses. Data link layer does not understand IP addresses. In the case of Ethernet, every NIC means network interface cards. Every NIC ever manufactured comes equipped with a unique 48-bit Ethernet address. How many bytes? 6 bytes, right? 6 bytes. 6 bytes, 48 bits Ethernet address. Manufacturers of Ethernet NIC request a block of Ethernet addresses from IEEE to ensure that no two NICs have the same address. to avoid conflicts. Should the two NIC ever appear on the same local area network, the NIC send and receive frames based on 48-bit Ethernet addresses. They know nothing at all about 32-bit IP addresses. The question now arises: how do IP addresses get mapped onto data link layer addresses such as Ethernet? How do IP addresses get mapped onto data link layer address such as Ethernet? That means the packet delivered to the data link layer. The how IP addresses mapped to MAC address. To explain how this works, let's use example figure 61. Two switched Ethernet lamps joined by a router. This is a router. It's a host 1, host 2, host 3, host 4. So 4 hosts, 2 switches. This is a switch, Ethernet switch. This is an Ethernet switch. It's connected with router. Okay. To explain how this works, let's use the example of figure 61, in which a university with 2/24 networks is illustrated. One network, for example, computer science department, is a switched Ethernet. It has the prefix /24. The other LAN and electrical engineering department, also switched Ethernet, has the prefix /24, but the prefix different. The two LAN are connected by a router. This is CS, this is EE. Then the two LANs are connected by a router. Each machine on the Ethernet and each interface on the router has a unique Ethernet addresses, labeled E1 through E6. E1 Ethernet, E2, E3, 4, 5, 6. Okay. And a unique IP addresses on CS or EE network. Okay, let's have a rest. Let's have a rest for 10 minutes. Have a rest for 10 minutes. Okay, let's continue. Let's start out by saying how a user on host 1 sends a packet to a user on host 2, host 1 to host 2 is host 1 to host 2 on CS network. Let's assume the header knows the name of intended receiver, possibly something like this domain. The first step is to find the IP address for host 2. This lookup is performed by DNS from the domain name to IP address, which we will study in Chapter 7. For the moment, we will just assume that DNS returns IP address for host 2. Then we get the IP address for host 2. The upper layer software on host 1 now builds a packet with this address 192.32.65.5 in the destination address field, and it gives it to the IP software to transmit. The IP software can look at the address and see that the destination is on CS network, its own network, because the host 1 and host 2 are in the same local area network. However, it still needs some way to find the destination's Ethernet address to send the MAC frame, to send the frame. One solution is to have a configuration file somewhere in the system that maps IP addresses onto Ethernet addresses. While this solution is certainly possible for organizations with thousands of machines, keeping all these files up to date is an error-prone, time-consuming job. So this solution is not feasible. It's not feasible. A better solution is for host 1 to output a broadcast packet onto the Ethernet, asking who owns IP address. The broadcast will arrive at every machine on the CS Ethernet, and each one will check its IP address. Host 2 alone will respond with its Ethernet address. In this way, host 1 learns that IP address is on the host with Ethernet address E2. So this is a better solution. The protocol used for asking this question and getting the reply is called ARP. So the ARP address resolution protocol adopt the second solution, broadcast and get reply. Almost every machine on the internet runs this protocol. ARP is defined in the standard document RFC 826. At this point, the IP address on host 1 builds an Ethernet frame addressed to E2 puts the IP packet in the payload field and dumps it onto the Ethernet. The IP and Ethernet addresses of this packet are given in the 61 not this given in this table. Okay, given in this table. Ethernet NIC of host 2 detects this frame, recognizes it as a frame for itself, swoops it up, and causes an interrupt. The Ethernet driver extracts the IP packet from the payload and passes it to the IP software, which seems that it is correctly addressed and process it. Various optimization are possible to make ARP work more efficiently. So, various optimizations. To start with, once a machine has run ARP, it catches the result. In case it needs to contact the same machine shortly, next time it will find the mapping in its own cache, thus eliminating the need for a second broadcast. So this is one optimization method. All machines on the Ethernet enter this mapping into their ARP caches. To allow mapping to change, for example, when a host is configured to use a new IP address, to allow mapping to change. So if the IP address changed, new IP address is configured to a host, but keep its own NIC. Entries in the ARP cache should time out after a few minutes. A clever way to help keep the cache information current and to optimize the performance is to have every machine broadcast its mapping when it is configured. Okay, this is the second optimization. To have every machine broadcast its mapping when it is configured. So every machine broadcast actively its new mapping. ARP as well as the other Internet protocols makes the assumption that hosts are configured with some basic information, such as their own IP addresses. How do hosts get this information? It is possible to manually configure each computer, but that is tedious and error-prone. There is a better way. It's called DHCP, means Dynamic Host Configuration Protocol. This is an application layer protocol. So just now we have talked about ARP protocol. So we should understand the principles of ARP and the optimization of ARP. Probably we have short answers for this kind of question. DHCP, Dynamic Host Configuration Protocol. With DHCP, every network must have a DHCP server that is responsible for configuration. When a computer is started, it has a built-in Ethernet or other link layer address embedded in the NIC, but no IP address. The computer broadcasts a request for an IP address on its network. It does this by using a DHCP discover packet. This packet must reach the DHCP server. If that server is not directly attached to the network, the router will be configured to receive DHCP broadcasts and relay them to DHCP server, wherever it is located. When the server receives the request, it allocates a free IP address and sends it to the host in DHCP offer packets. To be able to do this work, even when hosts do not have IP addresses, the server identifies a host using its Ethernet address. Okay, DHCP. About the DHCP, we should understand the function of DHCP. With DHCP, then host can get its network configuration algorithm parameters automatically. An issue that arises with automatic assignment of IP addresses from a pool address pool is for how long an IP address should be allocated. IP address assignment may be for a fixed period of time. A technique called leasing. Just before the lease expires, the host must ask for a DHCP renewal. DHCP is described in this standard document, RFC 2131 and 2132. It is widely used in the Internet to configure all sorts of parameters in addition to providing hosts with IP addresses. Now, then other techniques about IP we will not discuss in detail, such as MPLS, multi-protocol label switching, is previously close to circuit switching. MPLS adds a label in front of each packet, and forwarding is based on label rather than on destination address, making the label an index into an internal table makes finding the correct output line just a matter of table lookup. Using this technique, forwarding can be done very quickly. Forwarding can be done very quickly, so improved performance with MPLS. Okay, we will not discuss this in detail. MPLS enable is between IP and the PPP or other MAC header. So this is MPLS labels. Okay, now we will not discuss the other knowledge points because this is some complex for you. So, so much for the chapter 5. In this chapter 5, we have talked about addresses, IP format, addresses, IP address, IP address, IP address, IP address, IP format, packet format, packet format, packet format, then routing algorithms, routing algorithm principles. So IP address, packet format, and routing algorithms. So now we will review this chapter with with exercises. Okay. Okay, wait for a minute. Okay. Chapter 5 about network layer. I have these questions, choice questions, short answer questions, fill in blank questions, and the other comprehensive application questions. Okay, many questions in these chapters. Question 1. IP protocol provides A, B, C, or D. A. Virtual circuit and datagram service. B. Reliable and connection-oriented service. C. Unreliable and connectionless service. D. Reliable and datagram service. So I will distribute the answer sheet. Question 1. Okay, please take part in the answering questions actively. Okay, only one student and select C. Two students select A. Okay, the answer is C. The answer is C. IP protocol provides unreliable connectionness. So virtual circuit, no. Reliable, no. Reliable, no. So unreliable in the connectionness service. Question 2. Which answer? Question 2. Now, please consider question 2. Which answer is correct? A, B, C, or D? E. Yes. Right. The answer is B. Just now we have learned this point. To detect if host is reachable or not. Answer is B. Okay. Question 3. Question 3. Which one is correct? Question 3. Which one is correct? The total number of collision field. Which one is correct? C? C, that's the total number of collision field is C, 3. The total number of collision, this is a collision field. This is a collision field. This is a collision field. So the collision is C, 3. The total number of condition field is 3. Then total number of broadcast field. Then router depart the whole network 2 parts into 2 parts, 2 broadcast field. So this is the first broadcast field. This is a second broadcast field. So broadcast field, we have 2 broadcast field. So the answer is C. The answer is C. Okay. Question 4. Question 4. The checksum field in IP head is used to checking what kind of field? Question 4. Which one is correct? Question 4. Okay. The correct answer is B. IP head. The checksum field in IP head is used to checking only IP head. Okay, the correct answer is B. IP head, not the whole IP packet, not data field, not pursuit field, not head field. So the check IP head. Question 5. Okay, question 5. Which one is correct? Question 5. Which one is the answer? Question 5. A, B, C, or D is the answer. Okay. Two students select D. No, not D. Not. Okay. Question 5. The IP address is 172.16.7.131/24. That means if IP address occupies 4 bytes, that means /26/26, the boundary locates here. Here is 2 bits, right? 2 bits. Then from 2 bits, 3 bytes, it is 24 bits. Then 2 bits here. That is /26, right? So now that's term 131 into binary. 131 is 1 0 0 0 0 1 1, right? 131 is 1 5 0 1 1. So then /26 means this the boundary between the network portion, prefix portion, and the host portion locates here. So the broadcast address means these 6 bits in host portion set all 1. So the fourth binary is 1 0, right? Then followed 6 1, right? This is a host portion, 6 bits. For broadcast address should set with 6 ones. So turn this into decimal notation. Turn this decimal notation. This is 255 minus 64. So it is 191. So the fourth byte is 191. The answer is B. Do you understand? Do you understand? If you don't understand, I will explain this question next time. Okay? So much for today. Bye. So much for today. Bye. Okay. The answer is B.